Assalamualaikum. I'm CT-00007. I would like to present about relative risk for poverty in Kelantan, a Bayesian approach. Okay, we move to the introduction. Poverty is the worst problem that the world faces today. It has received much attention due to its effect, especially on academic achievement, economic recession, disease, alcohol-involved suicide, and suicide rate. Actually, wide-varying definition of poverty has emerged. However, this study will use the definition of poverty as income insufficiency, which is that the household's income fails to meet a poverty line that differs across the country. In Malaysia, poverty line income is different for Peninsular Malaysia, Sabah, and Sarawak. The level of PLI is 930 ringgit, 1,170 ringgit, and 990 for Peninsular Malaysia, Sabah, and Sarawak, respectively. Consequently, households with incomes below the poverty line are classified as living in poverty. Statistics have shown that the poverty rate has reduced from one year to another. However, the gap exists between the region, state, rural, and urban areas. According to the Department of Statistics Malaysia, Kelantan is known as the second highest incidence of poverty after Sabah in 2000. Modern data relate to non-overlapping area unit is a common problem in several statistic applications. This study used the response variable of poverty data, which is the number of poor household counts for each district, typically displays partial dependence, with observation from area units close together tending to have similar values than further apart. Bias in parameter estimates and overly optimistic standard error will occur if this autocorrelation is ignored. Apart from that, most studies overcome this problem by adding a set of autocorrelated random effects on the linear predictor of the regression model. These random effects are most common modeled by a conditional autoregressive model, which is CAR model, prior as part of a hierarchical Bayesian model. Therefore, the study will use the commonly used CAR model, which is Lerock's CAR model, with different neighborhood matrices to estimate poverty risk in Kelantan. Okay, next we move to the methodology of the study. First is a data description. That data on poverty were obtained from the eCASI database from the Ministry of Women, Family and Community Development for the year 2010. Why 2010 is chosen? Because the census of the household in Malaysia is performed for every 10 years, where 2000 was the latest census organized. The state of Kelantan is split up into 66 districts. The response variable that I use in this study is the number of poor household head, including hardcore poor for each of the 60 districts, which is the study region of the study. The covariate used in the study were the socio-demographic characteristic of the household head, including the number of female-headed household, average age, and number of non-education of the household head in each district. Next, I measured the standardized poverty ratio. The standardized poverty ratio was used to measure poverty risk. It was calculated for district K as SPRK equals to YK divided by EK. Here, YK denotes the number of poor household heads in district K, and EK is the expected number of cases, which is calculated as equals to sum of YK divided by sum of PK times with PK, where PK is the number of living household. The value of SPR above 1 represents district which elevated levels of poverty risk. However, elevated risks are likely to happen by chance if EK is small, which can occur if the population at risk is small. Okay, to overcome this problem, a Bayesian hierarchical model is adapted to estimate the poverty rates using covariate information and a set of random effect phi k. The random effect are included to account for the spatial autocorrelation that remains in the data after adjusting for the covariate. The random effects in this study were modeled by Leroy prior. The poverty data was fitted using Poisson linear Leroy scale model, which is given as follows. Okay, here from the model, RK denotes the risk of poverty in district K. The parameter rho takes value between 0 and 1. If rho is close to 1, the strong spatial autocorrelation in the data exists. A uniform prior is specified for rho where rho has uniform 0, 1. Here, WKJ denotes a measure of closeness between areas. Inference for this model is based on Markov-Chain Monte Carlo simulation using a combination of deep sampling and metropolis Hastings type. This study used car-bias software, which is an R package for Bayesian spatial modeling with conditional autoregressive prior. Okay, next, we move to the neighborhood matrices used in this study. In the spatial data, identifying the neighborhood structure of the data being analyzed is important when conducting tests for autocorrelation data and modeling data at the area level. The neighborhood matrix is an n times n matrix whose element WKJ represent a measure of closeness between area K and J. These elements can be binary or non-binary. In this study, the most common specification of W in the literature, including contiguity neighbor, Delaunay triangulation, and binary distant neighborhood matrices are considered. Actually, the contiguity matrix is defined by whether two spatial units share a border or not, where WKJ equals to 1 if area K and J share a common border, and 0 otherwise, while for the Delaunay triangulation, it is defined as WKJ equals to 1 if centroid of area K and J are connected by triangulation H and 0 otherwise. Lastly, for the binary distant neighborhood matrix, where WKJ equals to 1 is the Euclidean distance between the centroid of area K and J less than the threshold distance, which is the maximum of the minimum distance between each other, and 0 is otherwise. Okay, next we move to the result of the study. The variance inflation factor was used to measure collinearity among the variables in the regression model. It was found that there was no collinearity were observed between the covariates except for the number of female-headed households and the number of non-education of household head where the value of BIF is greater than 10. Apart from that, to reduce the collinearity between variables, the number of the female-headed household variable was transformed into a natural log. Thus, BIF become less than 10 and multicollinearity did not exist between covariates. The area units data tends to have spatial autocorrelation even after covariates were included, which was due to unmeasured covariates. So, firstly, a Poisson log linear model without any spatial structure was fitted to the poverty data to measure the existence of spatial autocorrelation of residual. Then the residual from the model were tested for the presence of spatial autocorrelation using Moran-Size statistic. The result of Moran-Size p-value was less than 0.05, which indicates that the residual of the model contained a strong spatial autocorrelation structure. Thus, the assumption of independence in the model was omitted. Then, a Poisson log linear Leroy scale model with 3 different neighborhood matrices was fitted to the poverty data. Okay, table 1 shows the result of the IC and RMSE among the W matrices. Okay, from the result we can see that contiguity and Delaunay triangulation has the lowest DIC and RMSE value. Therefore, these both neighborhood matrices perform the best in estimating the poverty rate. The effect of covariates are presented in table 2, 3, and 4. Here, table 4 here. Okay. This table displays the medians as well as 35 credible interval of posterior poverty relative risk for all 66 districts in Kelantan. Estimates are obtained using Poisson log linear Leroy scale model with different neighborhood matrices and average age, number of non-education, and number of the poor household head as a covariate. From the result, we can say that the choice of the neighborhood matrices has little effect on the result. Both the relative risk and credible interval were consistent across the 3 different neighborhood matrices. The household head age appears to be associated with poverty reduction, with a relative risk of 0.93 for 2 years increase in the average age of the household head. There is convincing evidence that an increase in the number of non-education of the headed household head by 62 is associated with an increased poverty risk by 21%, indicating that this covariate is a very informative covariate. Areas with a higher number of the poor female head of household were at high risk of poverty, with a relative risk of 1.12. Lastly, conclusion. This study explored the most commonly used conditional autographic prior distribution, which was Poisson-Log linear Lorentz model with different W matrices. Previous study commonly used contiguity matrix as neighborhood matrix. However, this study shows that the performance of Poisson-Log linear curve model with the long integration was almost similar to contiguity matrix. Therefore, both neighborhood matrices fit the poverty data best. Overall, Kosiel appears to have a higher risk of poverty than the other districts considered in this study. These differences in risk appear to be partly due to covariate, decreased number of non-education and female household heads appear to decrease the poverty risk. In contrast, increase the age of poor household head appears to decrease the poverty risk. This study found considerable differences in the smoothing properties of the Poisson-Log linear Lorentz model depending on the type of neighborhood matrices. This in turn had an effect on the ability of the models to predict the observed risk in an area. This result has significant implications for our researchers using Poisson-Log linear Lorentz models, since the neighborhood matrices chosen may markedly influence the finding of the study. Okay, that's all for my presentation. Thank you.